Dear students, today we will discuss the topic of a linear transformation in details regarding the general linear transformation, what are the rules for a transformation, and also we will discuss about the isomorphism of these type of linear transformation. Basically, for a linear transformation, what we required normally we require two vector spaces, and T is a transformation from one vector space to another vector space. For instance, we know that Rn is a vector space, Rm is also a vector space. Rn is n-dimensional, Rm is m-dimensional, and T is a transformation that transmit the vectors from vectors of Rn to the vector of Rm. And this is the nice property of a linear transformation is that behind a linear transformation, there is a standard matrix which are working and which are employing all the rules. This is the useful property of a linear transformation. And in general, if a mapping T satisfies these two conditions that T of u plus v is equal to T of u plus T of v, and moreover T of k times u is equal to k times T of u. If these two properties will be satisfies any map or any transformation, then we call it a linear transformation. And these are the if the proper definition. Whenever we have two vector spaces v and w and t is a transformation, you know that it takes the element from one space and shift it to the another space w. So t times ku is equal to k times t of u. This is called the homogeneity property, and the additivity property is T of u plus v is equal to T of u plus T of v. And if v is equal to w, if the vector spaces are the same, then this linear transformation is called linear operator. Now, if we extend this property, then we can see that this property is also equivalent to this property that T of K1 V1 plus K2 V2 is equal to K1 TV1 plus K2 TV2, where K1 and K2 are these are the any scalars. And moreover, if we write its general form of that one, then we will get this useful formula for a linear transformation that it always satisfies this condition T of K1 V1 plus K2 V2 plus up to KR VR is equal to K1 TV1 plus K2 TV2 plus up to KR TVR. And this formula is very useful to solve many type of a problems of a linear transformation. Even various numerical problems of linear transformation can be solved by using this important formula of a linear transformation. And this is the good result regarding the linear transformation that linear transformation always maps 0 to the 0. Like if we put the 0 from V, this first 0 and second zeros are different. Like because the first 0 is from vector space V and second 0 is belongs to the vector space W. So it means that they can be different because it's a transformation, and in transformation case, both spaces are different. Maybe it's in R2, the other one is in R3. But this statement is always true that T of 0 is equal to 0. And T of u minus v is equal to T of u minus T of v. And one can see that this simple proof of that one is because T of 0 is equal to, we can write 0 times u because 0 multiplied by any vector is equal to the 0. And by property of linearity, this constant can comes outside and T of u equal to the 0. And hence it's proved. And moreover, the second proof one can see that simply that it can be held in here. And then there are some examples of a linear transformation. Basically, behind the linear transformation, always there is a matrix. So matrix is a good example of a linear transformation because the sum of two matrices is a matrices, and from any matrices we can take scalar as a common. So that's why matrix transformation is a good example of a linear transformation. And the zero transformation is also an example. Zero transformation mean T of v is equal to 0. Whatever you put, the answer will be 0 belongs to the W. And it's also fulfilled the both conditions that T of u plus v is equal to, if we take 0, then you know that T of u is equal to 0, T of v is equal to 0, and T of ku equal to 0 because it's a zero operator or zero transformation. then one can say that T of u plus v is equal to 0, which can be right is equal to T of u plus T of v, and T of ku is also equal to 0. One can write as equal to k times 0, which is equal to k times Tu. Hence, these two properties are satisfied. This means that this operator is this zero transformation is a linear transformation. Identity operator is also a linear. One can see that it also satisfies these two conditions, and it's very simple. And then dilatation and contraction. So there are another two important type of a mappings, which are the linear, like T of x is equal to kx. And if k is less than 1, we call it's a contraction. Uh, T is like k is in between 0 and 1. And if k is strictly greater than 1, then we call it a del, dilation. Relation operator. And these two are also linear. One can see that it simply satisfies this condition that k can be taken as a common, and it fulfill the proof is available over here in the two steps. Now let's move toward the another examples of a linear transformation. For example, if T is a transformation from Pn to Pn plus 1, like all degree polynomials of n and all polynomial of degree n plus 1. Now, if you put T of P is equal to x time P, like x multiplied with each of its entry, then one can see that it will also satisfies T of Kp is equal to k times Tp. Like one can take k as a common from the outside, and it also satisfies this property of addition that T of P1 plus P2 is equal to T P1 plus Tp2. Like, and the proof is in simple steps over here. Another one can see the example from a linear transformation from an inner product, as the inner product will also gives us a linear transformation example. For example, if Tx is equal to x time v, where v is any vector, any fixed vector, then one can see that if we put T of Ku, then it will becomes Ku inner product with V, because the transformation is defined here. And if we use it, we know that K can be take a common from the inner product. If we take a K separate, then the rest of thing will be equal to T of U. It means T of Ku is equal to K times Tu. And moreover, T of U plus V is equal to T of U plus T of V. You know, the in inner product we have this additive property, and we can distribute into the two forms, and hence it means that this inner product using this linear transformation using inner product is a linear transformation. And then another example of a linear transformation based on a matrices, like if we take T of A is equal to A transpose, where A is any n cross n, a square metric of n rows and n columns. Then the first one is linear transformation, but second one is not. The first one, you know that if we can take a transpose of a transpose with k any constant, then k will come outside, and we'll take k outside, and then A transpose is equal to T of A1. It means it's fulfill the first condition. And now if we take T1 of A plus B, where A and B are two matrices, then it is equal to A plus B whole transpose, and there is a property of a whole transpose is equal to the A transpose plus B transpose, and hence it will be equal to T of A1 plus T of A1 plus T1A plus T1B. So it means that this T1 is a linear transformation. On the other hand, T2 of A is equal to determinant of A. If we define this way, then it's not a linear transformation. Why? It doesn't fulfill the both conditions. We know that here, like if we take Tk A, this is equal to the determinant of k times A, where k is any constant. And if we take the k common, then it will becomes k power n with determinant of A. Now, if n is equal to 2 or 3, then that is not equal to the k times t A2. It means this is not a linear transformation. It not fulfill the first condition. It also not satisfies the second condition, because we know that determinant of a plus b is not equal to determinant of a plus determinant of b. So we cannot write T2 of a plus b is equal to T2 of a plus T2 of b. Hence, it doesn't fulfill the both conditions of a linear transformation. And this is also the good example of a linear equation or straight line. Normally, the all linear equations are not a linear transformation. Only those which are passing through the origin are a linear transformation. For example, if we take Tx is equal to x plus x naught, so this x naught make a problem if it is not equal to 0. Like all those lines which are passing through the origin, that are only the linear equation, linear transformations. Because linear transformation gives 0 equal to 0. And if you put over here 0, then it is equal to x naught. And if x naught is not constant, then it means it's not satisfies the linear transformation condition. Now here there are some other evaluation transformation. Like if we take T of f, where f is a collection of all functions, like real valued functions, and Tf if we define f of x1, f of x2 up to that one, then like T is a transformation from V to Rn. V is a subset of all functions, real valued functions. Then we can see that this T of if we take Tf is equal to in this form, then we can get its distinct values by getting this evolution transformation. And it also fulfills the condition of a transformation. Like one can see that T of f plus g is equal to Tf plus g, and T of kf is equal to k times Tf. Like it will be separable like this one because it's placed like as a vector, and from the vector we can take constant as a common, and the vector we can split into the two forms. Then this is the property as we already described, that linear transformation we can split into that of the form where V contains the basis of that one, and this will gives us sometimes to make a useful formula to get the values of these ones. For instance, if V1, V2, Vn are the basis of a V, then the image of every vector can be expressed in this form. Like, look, if V is like one can see that we know that V1, V2 up to Vn are the basis of that one. So it means every element uh, V in V can be expressed as a linear combination of V1 plus V2 plus V3 up to Vn. So it means we can write V is equal to C1 V1 plus C2 V2 plus up to Cn Vn. Then if you apply the T on both sides, then it will becomes C1 TV1 plus C2 TV2 up plus up to Cn TVn, where C1, C2, C3 are the constant. And this will be gives us the same thing which will be very useful, and we can get different form of a formulas. For instance, there is a very nice example in this regard. Look, in R3, V1, V2, V3, these are the bases of R3. And suppose that there is any transformation T from R3 to R2, which is a linear transformation that maps TV1 to 0, 1. And if we put T on V2, then that is 2 minus 1, and the image of V3 is like TV3 is equal to 4, 3. Then the question is, what is the general formula of Tx1, x2, x3? And moreover, by using this formula, compute any value, for example, T of 2 minus 3, 5. We can find this value by the formula when it will be when we compute it. Now, this is the simple technique for that to find it. For example, V1, V2, V3 are the bases of R3, and we know that for any x1, x2, x3, we can write this x1, x2, x3 as a linear combination of this V1, V2, V3, the basis of element, because basis can be generate every element of a vector space. So for general x1, x2, x3, we can write c1 v1 plus c2 v2 plus c3 v3. Now, if we multiply these and make into the linear system form, then it will become three equations, and we can find its solution by any method, by elimination or by salt substitution method or by Gauss-Jordan method, or any method we can employ to get the value of C1, C2, C3. It means x1, x2, x3 is equal to, one can see that it will be the value into the form of x1, x2, x3, and it means this is the values of this one. Now we know that t is a linear operator. If we apply t on both sides, then t can be split into this form, like t of, we know that t of v1 plus t of t will be split into that one, as we know the above formula, like it will be split into that parts. So this x3 will comes out, x2 minus x3 will comes out, and also plus t x1 minus x2 will also come out with t of v3. Because of that one, just we apply the t on both sides. Now we know that t of v1 is already variable, that t of v1 is given as a 1 0. So we just plug the value 1 0 over here. T of v2 is 2 minus 1 is already given. T of v3 is also variable 4 minus 3. And by simply solving this one, the first element with first and second element with second, we will get this equation. It means t of x1, x2, x3 is equal to 4x1 minus 2x2 minus x3 and 3x1 minus 4x2 plus x3. So this is the formula for a this transformation. It means this linear transformation will be into the general form of that one. Now we can find out any value by using this formula. For example, if we want to compute it at 1 0 0, we just put 1 0 0 over here and get the value. And if we want to compute 2 minus 3 and 5, just plug the values over here. In place of x1, x2, and x3, we will get the value 923. So one related example is also available in the assignment question. For example, here you need to, it's available that t is a linear operator from R2 to R2, because it's an operator, because its domain and range sets are the same. And by using this formula, we can find out the value. If we can find the formula, and also we can compute the value of t at 3 minus 2. And moreover, here there is also one of the related problem is available over here. One can compute it. Okay, now there is also another example of a linear transformation, is that one, that this differential operator is also linear. Like we know that derivative of f plus g is always equal to derivative of f plus derivative of g. Moreover, derivative of kf is equal to k times derivative of f. Here there is some typo. Like you can see that these two are equal, and this one t derivative of f plus g is equal to derivative of f plus derivative of g. These are equal. Okay, so there is just typo. It will be just take on the other side, and these two will be close always, because differential operator is also a good example of a linear operator. Moreover, this integral transformation is a linear transformation. Like if we want to integrate anything, like integration of f plus g is equal to integration of f plus integration of g, and integration of k times f is equal to k times integration of f. So this will also satisfy this condition. So it means integral transformation is also a good example of a linear transformation, and we can use it always to compute the different values. Then the next thing is important regarding two important subspaces. One is called the kernel and one is called the range. Now, if T is a linear transformation, then the set of all vectors V that maps 0 to 0, that's mapped into the 0 is called kernel of T. Like, for example, if we put, we know that T of 0 is equal to 0, but there are some other values of vector space V that also whose image is equal to the 0 in vector space W, then that elements belongs to the kernel of T. Mean kernel of T is the collection of all those element of V whose image is equal to the 0 in W. And the set of all vectors in W that are images under T of at least one vector V is called the range of T, and it is denoted with the range of T. So range of T and kernel of T, these are also the two important sets, and we can see that these two are also a subspaces. Now, but first of all, the kernel and range of a matrix transformation. If T is a transformation from Rn to the Rm, then we can see the null space. Null space means collection of all those elements whose image is 0 in Rm. So also the range of T is the column space of A. Behind the linear transformation, there is a matrices. So this is the same idea which is equivalently present, equivalent over here. Now, one can see the simple example, like if T is a zero transformation, like T of V is equal to 0 for all V belongs to the vector space V, then we can see that every element of vector space V image is equal to the 0. It means kernel of T is equal to entire set V, because every element V, if we put in T, then its image is 0. So in that case, kernel of V is equal to kernel of T is equal to the V. And one thing more is that since the for every element of V belongs to the V, the image is only the 0. It means as every element is 0, uh, for every element from vector space V, the image is 0. So it means the range is only 0. It contains range of T, it will be only the single element 0. Now, the kernel and range of a identity operator, this is also a good example to understand that what is the kernel and what is the range. Like identity operator behaves like T of V is equal to V. And one can see that the range of I is entire set V in that case, and the the kernel contains only the 0, because 0 is the only element that maps to the 0 in case of identity operator. So kernel of I is 0. And you have to notice that the V is a vector space, so Ri is also a vector space. And this kernel set is 0, so 0 set is also a subspace. This is a subspace of V in that case. Now, this is also some other examples, range and kernel and range of orthogonal projections. Like, for example, if we want to move the element to the x-axis, then kernel of T will contain all those points which are of the form 0, 0, z for all values of z in R. And in that case, one can see that the range of T is equal to x, y, and 0. And note that if we combine these two collections, then it will becomes the entire space R3. So it means there will be a relation between the kernel and the range with the dimension of a with the entire space R3 or the dimension of a R3. Now we will comes to that one. So there is kernel and range of a rotation linear operator. If T is operator that rotate the elements for every vectors in the xy plane with some angle of a theta, then one can see that in that case the range of T is equal to the RT, because all elements will be moved. And in that case, 0 is only moved towards the 0. So it means kernel of T is 0 in that case. So this is also another example, kernel of a differential transformation. One can see that a differential transformation, we can identify what is the kernel of that one. So kernel will obtain the 0 towards the 0, and moreover, if we take derivative of any constant function, then its derivative equal to the 0. It means all the constant maps belongs to the kernel of T in that case, or kernel of D. Now, this is the most important result in that direction, that if T is a linear transformation from vector space V to W, then kernel of T is always a subspace of V, and range of T is also a subspace of W. One can see that kernel of T, since kernel of T contains all those elements whose image is equal to the zero. Now, if V plus V1 plus V2 belongs to the kernel of T, then one can see that T of V1 plus T of V2, since this is a linear operator, so we can split into that form. And T of V1 equal to 0, T of V2 equal to the 0. And hence it means uh, V1 plus V2 also belongs to the kernel of T. And moreover, if V1 belongs to the kernel of T, then T of KV1 can be written as K times TV1 because T is a linear operator. And K will be separable, and we know that K of V1 equal to the 0 because V belongs to the kernel of T, then K times 0 equal to the 0. It means KV1 also belongs to the kernel of T. Hence, it means that kernel of T is a subspace of vector space V. Similarly, the range of T is also is a subspace of W. So one can see that it will also satisfy this condition, and one can simply prove it that one. There are some applications of differential equations of that one. We just skip that this application. There are a variety of application of linear transformation, but in this course, these are not related to. Uh, these are not related in the into the these are not included in the syllabus. So let T is a linear transformation from vector space V to the W. If range of T is a finite dimensional and dimension, then its dimension is called rank of T. Basically, rank is the number of non-zero rows in in echelon form of a T. One can see of that one, but the rank of T will also gives us the range of T in case of a finite dimensional. And if kernel of T is finite dimensional, then dimension is called nullity. Like range of a the kernel of T, the dimension of kernel of T is called nullity because range of T is subspace, and kernel of T is also subspace, and in case of finite dimensional it must have a dimension, and in that case it's called the rank of T and nullity of T respectively, where when the range of T is finite dimensional and kernel of T is also finite dimensional. And this is also the pillar formula of a linear algebra. In that case, the nullity of T plus rank of T is equal to the n, where n is the number of columns of T, or n is the total number of and the dimension of a vector space V. So this is the important formula, and this is also related to the nullity plus rank is equal to the n, for a matrices as you saw before. But in case of a linear transformation, it's also true because behind a linear transformation there is a matrix. So that's why this equivalent formula is also available over here, and we can use it to get the different values and for the different kind of examples for the computational purpose. Then there are some important statements for true and false regarding that one. If T of C1 plus CV1 plus C2V2 is equal to C1V1 plus C2V2 for all vectors V1, V2, and for all scalars C1, C2, then T is a linear transformation. Yes, because it's also the equivalent form of a statement of a linear transformation. So if this is true, then that statement is also true, and this is its equivalent form. And if V is a non-zero vector, then there exists exactly one linear transformation that maps T of minus V1 equal to minus V1. So for non-zero vector, this will not be always a unique element. For that one is satisfied. For instance, there are the some other linear transformations that also satisfies this condition. for the non-zero vector. So this statement is not always true. There is exactly one linear transformation T for which T of u plus v is equal to T of u minus v for all vectors u plus v. Yes, and the zero is only the operator T of zero. Like zero operator will satisfy this condition, and it's a unique for that for all u and v it is true. And if v1 is non-zero vector, then the formula defined as a linear operator. So if v is non-zero, then it will never be linear operator because this v naught make a problem. So v naught must be zero. If v naught is zero, then this will become a linear operator. The kernel of linear transformation is a vector space. Yes, kernel of a linear transformation. Kernel is always a vector space or subspace, and range is also a range of a linear transformation is also a vector space or subspace. Now, if T is a transformation, linear transformation from P6 to M2 cross 2, then the nullity of T is 3. Nullity is number of non-zero rows in nullity this need to be compute and see that is it will it becomes 3 or not. That if T is a transformation M2 cross 2 defined as a T of A is determinant of A, then it's not a linear transformation because determinant of A plus B is not equal to determinant of A plus determinant of B. If T is a linear transformation from M2 cross 2 to M2 cross 2 defined by T of A in this way, then its rank is 1. The rank means number of non-zero zero rows in echelon form. So if we can see that here rank is 1 because the first row, if we multiply with the 2 and subtract with the second row, then it will becomes the second row will becomes 0. Then it means the rank is equal to the 1. Then it means this statement is true. The rank is 1. And the rank is 1 also, it means that uh, if rank is 1, then it means uh, like the range set of the in that case it has a rank 1, so or dimension 1. So here we can use this like one can verify that if you apply simple elementary row operation on that one, so the only non-zero rows is 1. So 1 comma 3 is the only remains same and the second row will become 0. It means rank for this linear transformation the rank is 1. This statement is true. If it comes to the
Sorry,
some,
sir, before you
yes, please.
proceed, on question 3, on G, number G,
Okay.
um, I didn't get what you said. So is it true or false that the nullity of T is 3?
Yeah. Okay. Like, look,
Uh,
T is a transformation from P6
yes,
to M2 cross 2. Look,
yes.
here the dimension is 6 and here the dimension is 4.
Oh,
Okay,
okay.
like M2 cross 2 dimension is 4 and in sorry in P6 the dimension is 7. Why? Because you
It's
know
a
the
polynomial,
polynomial of degree
6
6, so
degree.
dimension
Yes,
is n
yes.
plus 1, which is 7. And
Okay.
we know that here
Oh,
the
yes, yes. That formula, rank
7,
of,
yes, if
yes,
you have
okay.
7 over here and here
Yes,
you have a 4, then
yes.
the
7
nullity, we know
minus
that
4.
nullity plus
Yes.
rank is equal to the n.
The
N mean number of
dimension,
a
yes.
total dimension of a P6, which is
That's
7.
true. Yes.
Then it
Okay.
means the nullity will be 3 and rank mean rank is 4. The
Yes.
4 7 minus 4 is 3.
Okay,
That means
great.
it is true.
Yes.
This statement is true
Okay.
because 7 minus 4 makes 3 and it will be the base on a this important formula, the nullity plus rank
Yes.
is equal to the n.
Yes, yes.
Okay, so n is
Oh, thank
basically
you.
the dimension of a vector space V. So it means it must be equal to 7 in that case, like
Yes.
because you have. this one.
Okay, thank you so much, sir.
Okay, perfect. Okay, good. So I think for the isomorphism, it will based on the next one that we will cover it later on. But here, if we will see some problems related to that one, we know that this problem is simple and one can solve it if you have a basis available. Then V1 is available, V2 is also available, and we know T of V1 and T of V2. Then we can use it to find the formula t of x comma y and also compute the value of t of 3 and minus 2. And here there is a t is to be the multiplication by matrix T. It means t of x, y, z is equal to the a times x, y, z. Here you can just multiply with that one and get the values of that linear transformation. It means this t is a operator from R3 to R3, and then find the range of T, like what is the range set, what is the kernel, and from the range of T and the kernel of T, one can find the nullity of T, nullity and rank of T, and nullity and rank of A. Basically, you know that rank of T and rank of A and nullity will be same because behind the linear transformation there is a standard matrix. Like this matrix is also called a standard matrix of a T. Like in the next problem, if A is a matrix of 4 cross 3 with rank 3, then what is the dimension of a solution space AX equal to the 0? Like if AX equal to the 0 means uh, we are asking about the nullity, and we know the rank nullity plus rank is equal to the total number of a the dimension of a vector space n, which is 20. Like here you can see that what it will be the values. It's just simple use the formula nullity plus rank is equal to the n, one can get this one. And here if ax equal to b is consistent for all vectors b in Rn, like is this consistent or not? Consistent mean it has a solution or not for all vectors b in R4. So this is also one can see that if it's not consistent, then what happened in that case? So this is the problem, like you can identify its solution. And if v1, v2, v3 are the vectors in vector space V, and if T is a linear transformation from V to the R3, and it is available that it's a linear transformation, that TV1 is this one, TV2 and TV3. Now, by using the linearity, just find out the T of 2V1 minus V2 plus 3V3. We know that if T is a linear operator, then it will be equal to 2 times V1 minus 1 times TV2 plus 3 times V3. And we know that T of V1, T of V2, T of V3 are available. Just plug that values and we can simply compute this value T of 2V1 minus V2 plus 3V3. So these are some simple examples regarding that one. If you have any other question, then you can ask your question, please. Okay, if there is no question, then we stop over here. And then in the next session, we will see the isomorphism and a composition of a linear transformation. Okay, thank you. Okay, bye.
Thank you so much, sir. Have a great day, everyone.
Okay, thank you.
Thank you. Bye.